So this is something probably I omitted when we talked about electric fields. I skipped chapter 5 in Jen's textbook. But I'm trying to include the results. So this is called Poisson's equation. Okay? So this is fish in French. I tried to learn the pronunciation, Poisson. Okay, this fish. At this point, we're trying to borrow the results from electric fields. This is a known equation, right? Divergence of E is equal to the charge density divided by the vacuum permittivity. But think, if we move this negative sign to the right, this is exactly what we're trying to work on. You have a scalar quantity and you have the Laplacian operator, which equals to a negative quantity. Again, I'm drawing a one-to-one correspondence between the E field and magnetic field. Right? So this is called the scalar Poisson's equation. Do we need to solve it? We don't really need to solve it. Why? Why not? Because we already learned Coulomb's law. Coulomb's law tells us, well, if you know the current density distribution as a function of space, you can try to find V. Right? So take a good look at this Poisson's equation. Even though I did not cover it, the reason is very apparent. If you know how to use Coulomb's law, or this is not directly Coulomb's law, right? Coulomb's law is relating rho to E, but this is something we also derived, we covered. So once we know this relationship, the electric potential can be acquired by direct volume integration of your charge density. This is a solution to the Poisson's equation. Okay? Now, what do we have to do to know the solution form for AX, AY, and AZ? Take a good look. For electricity and magnetism, basically you are solving the same equation in the same form. They're all called the scalar Poisson's equation. The only difference is now in magnetism, you are dealing with current density as a function of space. In electricity, you are dealing with the charge density. Second difference is in V, you have the vacuum permittivity in the denominator, but now in magnetism, you have the vacuum permeability in the numerator. That's the only two differences. Right? So in the end, by introducing A, we have the capability to reduce the problem to solving three scalar Poisson's equations. And Poisson's equations have well understood solution form. One by one analogy tells us if we know the X current density component, then we now know the AX component of the vector magnetic potential. We only have to perform the integration, the volume integration, borrowing the solution form of our known electric potential. We replace rho by J, and we replace 1 over epsilon 0 by mu 0. That's it. This is a major step, a major leap, right? We can already know A once we know J. So we combine these three sets into one simple equation. The volume integration of current density divided by the distance multiplied by the vacuum permeability divided by 4 pi directly gives us A. Okay? So this is like finding North America. Right? You should be excited because given any current density distribution, we now can calculate A. Once A is calculated, we only have to perform its curl to arrive at B. But all the filming staffs in my TA did not look excited. Why not? Because they still call this byproduct. Okay? Remember, what is my overall pursuit? My overall pursuit is, if given some arbitrary current density distribution, I can calculate B directly. Okay? So somehow you are the Portugal kings. You still remember the initial aim is to find India and not North America. Okay? You're good. You're smart. So we had to find a way to arrive at B directly by knowing J. Okay? That's the ultimate path. So even though we're already excited, by knowing J, you can arrive at A, but I mean, it's still A, right? It's a middleman. It's not the direct result. It's a byproduct. And if you are in this field early, even though you might not be so smart, you don't have a very keen insight into the physics, but you're very good in mathematical derivation, you can earn your name by doing that. Okay? So again, two French scientists, Biot-Savart, they did exactly the same thing. They probably went on a class and the professor taught them, well, you land in North America, right? That's it. Once you have A, you perform the curl, you get B. So what they did exactly to use this form and perform curl of A. Okay? Curl of A. So once you have this A, you perform curl of A, you arrive at B. But in that process, after their solution, you find the direct path to arrive at B starting from J. Okay? So this is called the Biot-Savart law. Okay. They were thinking, initially, this integration is a volume integration. Remember, this is the volume integration for current density. If you think about it, you should be puzzled. examination 1 and 2 is coming up next Monday, right? What is current density? Current density is the surface density of current. Is there any meaning to perform the value integration of current density? It's weird, right? Ideally, J is I divided by area. So J has a unit of amps per meter squared. So what's the physical meaning to have a value integration? So to me, the major contribution of Biot and Savart was to realize, well, the basic current conducting element is a closed loop of wire. Okay? So you're trying to perform the value integration of that wire, that closed loop formed by a wire, a conducting wire. So they somehow performed the integration, the value integration. They reduced the value integration into a closed loop line integration. How were they able to convert the value integration, a three-dimensional calculation, down to a one-dimensional line integration? They realized the fact this loop is made of a conducting wire. So that conducting wire has certain area, right? So this value integration can be written as the surface, which can be viewed as a constant, times the differential length. So the differential value is the area multiplied by the differential length. So J times S is equal to what? The current. So now the integration is really reduced to a one-dimensional integration, right? That's the major contribution from these two scientists. Okay? All right, so if we have some current conducting closed loop, we only have to perform the closed loop integration of the differential length. So again, if you still remember, I spent so much time teaching you differential length, differential surface in vector analysis for apparent reasons. In different coordinate systems, you need to know how to properly formulate differential length. Otherwise, you cannot master magnetism. Right? So here, I have I. Okay? So if I know the current being conducted in a closed loop conducting wire, I can perform the closed loop integration to find A. But they were not satisfied just in knowing A. Just in knowing A cannot make you famous, cannot make you remembered. Okay? You have to do something else. You have to perform the curl operation. Because they understood the value to be able to directly achieve B from J. Okay? In another word, they want to have a counterpart of Coulomb's law. Okay? So up to now, I can say this is BS, Biot-Savart. This BS is not that BS, okay? All right. So all you have to do is perform the curl operation. They performed a direct and brutal curl operation. They really performed the curl on A. So you have to respect them. My mathematical skill is not that good. I would never dare to perform direct curl on the generalized solution form. But for you to remember and understand, pay attention to how the coordinate systems are labeled. The prime, we are trying to perform the closed loop integration of the current conducting loop. We're always using the primed system to denote the source. Here, the source is a current conducting loop. But this curl operation is trying to perform the curl at the observation location, which means I have a current conducting loop which sets up some vector magnetic potential A at my observation point. Right? So A in space is labeled by the unprimed system. But the current source is labeled by the primed system. Okay? So this current loop generates some A distribution here. Once I know A here, I perform its curl. This curl operation, pay attention. Once I know A here, A is the result of the current conducting loop, which is expressed by the primed locations. But once I know A, I'm trying to find the resulting B by performing the curl. This curl is only depending on my observation point. It's no longer associated with this current loop. So this curl operation is only operating on the unprimed system. Okay? Why do I care so much? Because this DL prime means the differential length, differential segment on the loop. Right? So this curl operation now operates on 1 over r. 1 over r is the distance vector, right? Which is sensitive to both the unprimed location and the primed location. The primed location means x prime, y prime, z prime to denote a space, a point on the current loop. So by now, I have curl operation on 1 over r times the differential length on the loop. So basically, these are two different quantities. This is a vector, 1 over r is a scalar. So I have to borrow the vector identity from the textbook. Okay? So if I perform the curl operation on the multiplication of a scalar and a vector, that can be decomposed into two parts. That's fine. Whenever I add complexity, I find functionality, right? So I have a new form, but look at this equation. You should be very happy because if we know current, hey, it guarantees us to arrive at B directly after some mathematical manipulations. But we have two terms from the vector identity. Now, smart students like you would understand why I emphasized on the primed system and the unprimed system. The curl operation operates on your observation point. It does not care about your source coordinate. So this curl operation, does it affect DL prime? dl prime is the primed location. It does not really care about it. But this gradient does operate on 1 over r. Okay? So basically, this term can be dropped. This is the desired result. Okay? So in the future, if we know the current in the form of a closed loop, all we have to do is we perform the closed loop integration of the gradient of 1 over r, making a cross product to the differential length on the conducting loop, and multiply by this. So this is the direct way to knowing current arriving at B. But Biot and Savart does not earn their name by stopping here. Okay? They earn their name by knowing, well, in Cartesian coordinate, 1 over r is this, right? Your observation point minus each differential segment, right? The sum of a square, and you take the square root, that is the distance r. Now, how to perform the gradient? Gradient in Cartesian coordinate is just direct differentiation to x, y, and z, right? That's what you have. Basically, in Cartesian coordinate, gradient of 1 over r is equal to the negative of your distance unit vector divided by the distance squared, or the distance vector divided by the distance cubed. So now this is, and then dl gradient cross dl is negative dl cross this, right? So this is the Biot-Savart law. You have two forms depending on how you write this term. These two are equal, but you can say this is the unit vector divided by r squared, or the vector divided by its distance cubed. Okay, so you have two forms. Once you know the basic current conducting element geometry, all you have to do is perform the closed loop integration. You arrive at B directly. All right, so let me copy this result for you. Right? So we spent so much time eventually our initial motivation was to be able to calculate B field by knowing the current distribution. But Ampere's circuital law is difficult to use. I mean, if your current distribution is arbitrary, non-uniform, right? So somehow, invoking mathematical null identity, we defined A. A is, the curl of A is equal to B, right? And then we started to solve. And we came up with 3 sets of scalar Poisson's equation, and we combine them into this one. So this is telling us, well, if you know the current density distribution, we can find A first and then perform its curl to get B. But Biot-Savart saw the possibility to really operate curl on this generalized form. Okay? So in the end, magnetism has a one-to-one counterpart to electricity. Ampere's law compared to Gauss's law, and now Biot-Savart compared to Coulomb's. Okay? Now, this is a better side-by-side comparison. What is Coulomb's law? In the past, we spent a lot of time, right? Coulomb's law tells you, well, even though we know that in real life, for electricity, we have the E field and we have the electric potential V. But once we know the distribution of the charge density, using Coulomb's law, we are able to arrive at the E field intensity directly without the need to know V. So V can be viewed as a byproduct, North America. Okay. And this is India, right? At the same time, for magnetism, I together with dl prime, this is a differential segment on your current conducting loop. So together, you know how your current is formed. Using Biot-Savart relationship, you can directly know B without the need to find A first. In a one-by-one analogy to electric field. Okay? So the main contribution of Biot and Savart is, well, even though we defined A, but A is pretty superficial, even though we understand the physical meaning of A as compared to B, B you have to perform a surface integration to find the magnetic flux. A, you only have to find a closed loop integration. But still, it's not so direct and not so straightforward, right, to understand A. So they are saying, hey, even though it's there, let's forget about A. So in the future, whenever you have current, we find B directly. And that's it. Okay? So in my personal opinion, I think the ability to calculate A or not is really, up to you. Okay? A is really not that well defined. As we mentioned, divergence of A can be chosen arbitrarily. So the meaning of A is really, vague. Okay? It's there mathematically because we want to be able to solve B directly from current. Okay? So let's stop here.